Thank you. My name is Jonathan. I am a applied ML intern on the AI Eng team, well, with the other interns. And I'll be presenting my work on automated speech recognition and specifically how we can turn this technology into microservices. So over the course of my 4 months, I've spent in my time in 3 main categories: investigating currently existing open source solutions, experimenting with fine-tuning ASR models to improve results, and building a open source reference implementation for what I believe could be a viable ASR microservice. So why are we addressing this problem? So automatic speech recognition is currently dominated by 3 main players in the space, which is our Amazon SageMaker, Google's Inference Machine, and Microsoft. And since we are aiming to target small, medium enterprises, these services are often priced well out of budget, and they're also very general. So the services that Amazon, Google, and Microsoft offer are trained on very large general models, so they fall short in terms of when you want to apply them to specific domains such as healthcare or insurance. So the overall goal of my term was to make a high quality speech recognition service available to all. And the solution that myself and Deval, who is not here today, came up with was to build a reference implementation and provide a tutorial on how another enterprise or ourselves could build one of these out of purely open source systems. So to start, I evaluated Caldi. So Caldi is a very popular ASR toolkit that's built out of C++ and is run via shell scripts. The problem with running on shell scripts is it's a very high barrier to entry when you're just trying to build a simple microservice. I then evaluated NVIDIA Nemo. NVIDIA Nemo is a very useful tool as it obscures the shell scripts from Caldi, but it's fairly low level compared to what I'll talk about next called Speechbrain. And it's also hardware dependent. So if we want to build the service, we are dependent on having NVIDIA graphics cards available to us. And finally, I evaluated Speechbrain and Hugging Face, which were developed sort of in tandem, or Speechbrain was built on top of Hugging Face. So still in active development, growing community. It offers many pre-trained models on their model hub, and provides all the tools to train new models and fine-tune old ones. So what is Speechbrain? Speechbrain was developed by Mila in Montreal, headed by Mirko and Tituan. It's completely open source and it's still active and it's a growing community. I'm now a member of their discourse. And it has everything you need to build a new ML ASR model. So data loaders, experiment automation using their brain class, build neural networks, tokenization, inference, much more. So I just included a screenshot of their documentation. And as you can see, it's fairly comprehensive in terms of all the tools it makes available to developers. So the microservice architecture I decided on and sort of analyzed was a pub-sub approach or a hybrid pub-sub approach. So while through my testing of the other services, I realized that inference can take a while, even for very short audio clips that we want to turn into text. So I developed this queuing system where users can send a job or task to our queuing API, which returns back to them a pub-sub topic, which they can then subscribe to on a RabbitMQ message broker. So once the task passes through our pipeline, which includes domain detection, which I'll get into later, and language detection, we can return them back to results when they're ready instead of having their API or their client polling for results repeatedly, which might take a significant amount of time. Also storing all of our completed transcription results in a long-term document storage in the form of MongoDB. And this allows the users to come back later and get results, and us to build our own data set of sorts, where we can keep track of what we've gotten correct, what we've gotten incorrect, and use that data to further retrain models in the future. So just to touch on the domain detection. So a core feature of this architecture is the ability to take in audio files and sort of point them at what language model, which is what I use for demonstration purposes, different fine-tuned models. So currently in the system, we have 3 models. We have a French model, an English model, and a Spanish model. and you could send in any kind of WAV file you want. It will determine which language it is and point the ASR inference task at the correct fine-tuned model for that language. So this runs on top of a Python Flask server in front of a MongoDB NoSQL database with RabbitMQ pub sub message broker. RabbitMQ was selected because it's very widely used and completely open source. And similarly with Prometheus and Grafana, we want to use those to visualize our system to make sure it's running healthily, especially if we want to into a production setting. What's cool about the system and the way each inference engine works is it's completely modular. So currently running our 2 Speechbrain models and a Hugging Face-based model. So Speechbrain was using with 3 different inference setups. So the classifier, which is used to select which language you want to use, an encoder and decoder setup to actually perform the transcription, and another transcription service from another developer named Yonatas. In terms of the models actually being used in the system, we have a model developed by Taltech NLP. This is the language detection model, error rate of about 7%. The English model we're using is a convolutional, deep neural network. It's a neural network that uses connectionist temporal classification, which helps boost our accuracy, and that was trained via Speechbrain. And finally, Jonatas has trained a Spanish model that was used trained on Hugging Face transformers and has an error rate of about 8.81%. So that's sort of an overview of the whole ASR system we've built. So I want to take a moment to touch on the fine-tuning work I've done. So I was tasked with fine-tuning a French model. So I started with Le Benchmark 3K, also developed at by people who made Speechbrain. And it starts with an error rate of about 24%. And it was constructed on a collection of audio samples, including television, radio, and telephone calls, which were both scripted and unscripted, built on top of Hugging Face, and has 318 million parameters. I use this model and I fine-tune it on the Common Voice French dataset. And I also augmented the data by varying the speeds of the audio clips from 95 to 105%. And I got some very promising results. So we were able to drop the word error rate by about 10%, and the character error rate, which was unreported at the initial point, was only 4.78%. Then using a larger model, which has no baseline numbers attached to it, we were able to achieve a very good character error rate of 3.86% and a word error rate of 11.16. So this shows that we can use fine-tuning in ASR, and we can also use this to using expanded training data to help improve the performance of our models running in systems. And this links back to before, where we can build our own data set with our MongoDB. We can use that model to further tune our models later down the line to improve performance as the system is being used. So as we moved later into term, I wanted to look at how we could deploy this in a way that is easy for everybody. So I landed on Docker Compose. Docker Compose is a subset of Docker that allows us to contain multiple containers and put them together to make enhanced functionality. So I selected Docker because it's becoming very quickly an industry standard. It's containerization, so it makes it platform agnostic. So it's really good for reference implementations. And we can run it on our cluster. We can run it on a Google Cloud platform. We can run it on a AWS instance. And if we use container orchestration such as Kubernetes, we can use this to scale as needed. So what you will see in a demo, if we have time at the end, is that we can build a reference implementation of a end-to-end ASR microservice using solely open source technologies, which is very valuable as open source technologies are free, and which addresses our problem of being priced out of range. And the outcomes of this is I've produced an article outlining what I've done and the experiments I've ran and how the system was designed, and a reference implementation that will be going up on the Vector GitHub page along with the rest of the conversation AI project, which you guys will be hearing about tomorrow. So other people can clone the repo or reference it if they want to build their own systems. So I don't know if someone can answer how we are for time, if I can run a demo.
Yeah, you have a few more minutes if you want to go ahead.
Okay, so I'm going to new share. I want to share just my entire screen. Not possible. So I want to pull up here. We can look at the service as a whole. And so we can see the service is built up of 4 containers: a RabbitMQ container, a custom implementation of our own Flask server, the Prometheus metric logger, and a Grafana data visualization. So we can look into those parts individually. So here's our Grafana overboard dashboard overview. So we can see that we have no messages in our RabbitMQ broker. This Grafana dashboard is being fed data via Prometheus, which is logging on 2 ports. This port is for an experiment I was running earlier today, and the RabbitMQ instance, which is allowing us to perform pub sub operations. So I did only just spin this model up, and it does take some time to get going. So if I ask localhost to ping the server is available, it is available. So we can send a queue task option. This queue task option, we can send just the audio recording me saying the quick brown fox jumped over the lazy dog. And now this will, on the server, deploy the pipeline to sort of determine what language we're using. So we should receive English when this when it's done inferring on that, and it'll be put into a queue where our running ASR model will then decode the message, and then on our RabbitMQ queue, we will be able to get back our results. So this just takes a second to get going. If you look in the actual server itself, we can see that it's working on downloading the model that we're going to use for the inference on the language we're going to use. So this download only occurs once, and then once the service is running, it will run in memory until the service is shut down. So we detected that we are going to get an English response, and then we can go into our Grafana dashboard and see we have created a queue here, which means our message is ready to be downloaded from our get results API, which isn't actually in this current build. So I guess that concludes. I want to thank everybody for bearing with my demo and listening to my presentation.